Last class, we have seen regular grammar as a formal representation of a language, and today we are going to see what kind of a language is represented by a regular grammar. So, what class of languages is generated by the family of regular grammars? We can have a claim for that, saying the class of languages generated by the family of regular grammars is precisely the set of regular languages, which means any regular grammar represents a regular language. Also, for any regular language, there exists a regular grammar. So, there are two sides, and hence we can prove this claim by using two subclaims. Subclaim 1, the language generated by a regular grammar is regular. That means we have to prove that for any regular grammar, the language generated is a regular language. Subclaim 2, any regular language can be generated by a regular grammar. That is, for any regular language, we need to find a regular grammar generating it. And then the proof of the claim follows from subclaims 1 and 2, because subclaim 1 tells us that the language represented by an arbitrary regular grammar is a regular language, and subclaim 2 tells us that for an arbitrary regular language there exists a regular grammar. So these two can prove the claim, and in this class we will prove subclaim 1, and in the next class we will prove subclaim 2. Subclaim 1, language generated by a regular grammar is regular, and we are going to learn a constructive proof for it, and the construction is this. Given a right linear grammar G, one can construct an NFA with epsilon transition AG such that the language of AG is same as the language of G, where the notation AG stands for the NFA A generated from the grammar G. So we need to devise an algorithm for generating an NFA with epsilon transitions AG from a given grammar G. So consider an example right linear grammar. G is, it's easy to observe that G is a right linear grammar, and we need to devise a technique to generate an NFA with epsilon transition from this grammar, generating the same language as this grammar. So the first the production in this grammar is this. The question is, what you can do with this production in the grammar? So you can start derivation in the start simple, assuming that capital A is the start simple. This rule can be applied to derive the terminal string small a using the production. So in terms of the NFA, you can see that an input string small a is generated by the grammar. So we need to have an NFA, and that NFA should accept this input string. So what will be the corresponding NFA? Maybe we can draw it like this. So this NFA is anyway going to accept this string, and hence that's okay. So note that the variable in the grammar, capital A, is going to represent a state in the NFA, and that is true. Later you can see how it is coming. Every variable in the grammar is going to become a state in the NFA, and in addition to these states, some more states are required like this, which are not named now. And why I made this state a start state is because I know that capital A is the start simple of the grammar. So the state corresponding to the start simple must be made as the start state of the required NFA. Now see what you do for the second production. So what you can do with this production? From the start simple capital A, you can apply this production and derive small a followed by capital B. In terms of the NFA, you can say that an input string small a followed by capital X, which is a terminal string, is given, and as of now in the grammar, using the grammar, we have derived the first symbol of the string and you have this capital B as the variable. So naturally from this capital B I need to derive the remaining part of the input string. The question is, how will you represent it in the NFA? So in the NFA you can represent it like this. That means a step in the derivation like capital A is replaced with small a capital B can be represented or simulated by the NFA by a transition going from the state for A to the state for B with the label as small letter a. So that's it. This kind of a step can be simulated by a transition going from the state for A to the state for B with the label as small a. Now see what you can do for the next production, which is B is going to X. Note that B is not the start symbol, hence assume that you are in this stage of the construction of the NFA. That is, from the grammar you already have derived this sentential form and you already constructed this part of the NFA as we discussed in the previous slide. So now this production tells you that this capital B can be replaced by the terminal string X. So this is what you can do. Now the question is, how will you simulate this step in the derivation by the NFA? So basically this step means you need to go from the state for A to the state for B with as simple as small a. That's what we did. And here similarly in the RHS there is no variable. So you have to go to a newly created state. For what input? For the input string X. It's not just one symbol. It's a string of terminals. So basically you need a path going from the state for B to a newly constructed state, because in the right side there is no variable, to a newly constructed state with the label as X. That's what you do. Okay, for B goes to X, if there is no variable in the RHS, from B we need a path going to a newly added state with the label as X, and you need as many intermediate states as required depending on the number of symbols in X. Go to the next rule. Again, B is not the start symbol, and so assume that you are in this stage in the derivation. That means you already have derived the sentential form A is followed by capital B, and this is the corresponding NFA that you have generated, assume. And this rule tells you that the capital B can be replaced with small x followed by B, where x is a terminal string. So how will you simulate this step in the derivation? It's very similar, you know that. You need a path going from the state for B to the state for B, the same state. You need a self loop with the label as X, and not that X is a terminal string. So this is what you need. So it's actually easy to observe, and the last kind of production is this. Assume that you are already in this stage, and this production is telling you that from the current sentential form, you can replace this capital B with the RHS of this production. That's what I did. And now you have a step in the derivation. And how will you simulate this step in this NFA? You need to have a path going from the state for B to the state for C with the label as X. And B and C being variables in the grammar, we know that there are going to be states for B and C. So B and C are states in the NFA, and we need to add a path from B to C on X. And not that all the intermediate states must be new states. That is what we are going to do in the algorithm. We are not going to take any other state here. All the intermediate states are going to be the newly added state. And I hope abstractly you got what we are going to do. To make it more concrete, let us consider one more example. And here is a right linear grammar given. G is the right linear grammar, and AG is the NFA that we are going to construct. And not that this is a right linear grammar, and I have written this right linear grammar assuming that this is the language that we need. That is a set of all strings over AB without consecutive A's in a string. So a string can be generated by the grammar if the string is not containing consecutive A's, and that is the grammar. And believe me, that is the grammar, and you check it offline and let me know if the grammar design is wrong. Anyway, that doesn't matter for this discussion. So the question is, how will you generate the NFA for this grammar? And the first step is identify all the variables, and the variables are capital A and B, and make corresponding state in the NFA. Each variable is going to become a state here. And the next step is you need to identify the start symbol, which is capital A, and make the corresponding state the start state of the NFA. And now you consider each production and add the corresponding part in the NFA. This is the first production. So in the grammar, from the start symbol A, you can derive the terminal string small a using this production. And we have seen this kind of a production. We know that from the start state capital A, we need to have a transition for A going to a newly added final state. That's what you do. Because in the right side there is no variable, it should go to a newly added state. And because you derived a terminal string, it must be a final state. And that's what we do. And what is the next transition? Next rule is this. And in the grammar, from the start symbol, by applying this rule, you can produce small a, capital B. And how will you simulate this step in the derivation? From the previous discussion, we know that we need to add a transition from the state for A to the state for B with the label as small a. That is what you do. And now the next transition, next production, which is A goes to B. And in the grammar, from the start symbol A, you can replace A with capital B. That's what this rule is telling. So how will you simulate this step in the derivation? That means you need to have a transition from the state for A to the state for B without a label. Without a label means the label is going to be epsilon. So basically for this kind of a transition where in the RHS there is no terminal symbols, then you need an epsilon transition. Now the next transition, B is going to BAB, and not that B is not the start symbol. So assume that you are in this stage of the derivation. That means by applying production number 3, you already have derived this part. And now this rule tells you that you can replace this capital B with a small BAB. So now you have a step in the derivation. B is replaced with small BA followed by B, which means you need now a path, because this is more than one symbol. You need a path from the state for B to the state for here B again. So B to B you need a path with the label as BA. So this is what you want to have. Okay, it's very intuitive, and move on to the next. And this is very similar to this rule. We already know what to do. We need to have a transition going from the state for B to the state for B. That is, you need to have a transition because only one symbol. You need to have a transition for B. That's what you have. And now the last rule in this grammar, which is B is going to epsilon. And not that B is not the start symbol, and assume that you are already here. That means from the start symbol, by applying 0 or more productions for A, I have came into this sentential form. That is, I already have generated the terminal string X and I have the variable B in the current sentential form. So in the grammar, so in the NFA, you will be now in the state B, because if you are here having capital B as the variable, you will be in the state for B. And till now, what input is read is the string X. So X is read until I came into B. Maybe I read it like taking this transition, this transition, this transition, any number of times, and finally here in B. And till now, what I read so far is the terminal string X. And now what you can do with this production? With this production is telling you, you can just take off the B, because if you apply this production, I can take off the B and I am deriving the terminal string which I have already generated. That is, till now I have read X and I came into B, and that X must be accepted, and for that I have to make the state B a final state. That is, if there exists an epsilon transition, then make the corresponding state a final state in the NFA. And that's what we did. And so we finished constructing NFA for this grammar, and observe what the language is. You can see that A is accepted because you can generate A. And now whatever is accepted, you can see that it's not containing consecutive A's, because the only A transitions are this and this. After this A transition, you don't have an A transition immediately because you only have B transitions. Similarly, after this, that means two A's cannot be processed. All of the symbols can be processed. You can prove that this language is exactly this. So precisely the language is the language of the grammar, at least for this example. And this is enough now to prove this theorem, which tells us that given a right linear grammar G, one can use an algorithm to construct an NFA with epsilon transition AG, said that their languages are same. And you remember, this is the start symbol. So the given grammar has capital A as the start symbol. Please remember it for constructing the algorithm. Capital A is the start symbol. So by using the same example, we can try to collect the steps in the algorithm. The first step is identify all the variables and the start symbol. So you identified all the variables and the start symbol. You made a state for each variable, A and B, states are there, and you made the state for the start variable as the start state of the NFA. And so what we did is, this is the step. For each variable B in the set of variables, if you recall, this is the set of variables, capital line. For each variable in the grammar, make a state in the NFA. So make B a state in the NFA. And also make the start symbol as the start state. And that's what we did. And now you process each rules in the grammar. This is the first rule. We know that for this kind of a rule, we need to add a transition like this. A is going to small a, means in the RHS there is no variable. So for A, the transition should go to a newly added state. C is a new state. And C must be a final state, because in the RHS no variable means A is in the language. So C must be a final state. So now you can generalize and add the corresponding step in the algorithm, which is, for all rules of the form B going to A, you add a new state C to Q and add a transition from B to C with the label as A. And also make this C a final state. And that is what we said. Okay. And now you proceed to the next transition. And for that, the rule is A is going to small ab. And you know that for simulating this, you need to have an edge from the state for A to the state for B with the label as small a. That's what we have. And so you can write the general step in the algorithm. For all rules of the form, B going to small a capital D. Not that B and D are variables in the grammar, and hence B and D are going to be states in the NFA. You just add an edge from B to D with the label as A, and that's what I did. Okay, that's what we did. And the next transition is for this rule. And what is the rule saying? A can be replaced with capital B. That means from the state for A to the state for B, we need an epsilon transition. So that is the case, and generalize and say for all transitions, for all rules of the form B going to D without a terminal symbol here, you add a transition from the state to the state of B to the state of D with the label as epsilon, B to D with the label as epsilon. Okay, now the next one, B going to epsilon. We know that we have to make B a final state. We saw it in the previous discussion. So the step is, for all epsilon transitions, that is B going to epsilon, make B a final state. Not that F is the set of final states. And now before adding the going to the next step, because of space limitation, let me remove this part which is not required. So this is the next rule, which means capital B can be replaced with small ba followed by capital B, which means we need a path, because there are more than one simple. We need a path from the state B to the state B to B with the label as BA. That's what we did, BA. Okay, and in general, this rule can be like this. From the B, you can replace capital B with a terminal string X followed by a variable D. That means to simulate this kind of a rule in the NFA, you need a path from the state for B to the state for D with the label as X. So this is what you need. And how many intermediate states you need? All the intermediate states are going to be new states. How many are required is actually the length of X minus 1, because here the length of X is 2. So you need only one intermediate state. So in general, if there are k number of simples in X, k minus 1 intermediate states are required. And now we can generalize this and add this step. For all rules of the form B going to X followed by capital D, you add a path for X from B to D with the label as X. And how many intermediate states are to be added? N number. N is equal to length of X minus 1, number of simples in X minus 1. And that's what I said. And now the only remaining step is for this kind of a rule, that is B going to X. It's very similar to this, but in the RHS there is no variable. That means now you are going to generate a terminal string, because in the RHS there is no variable. That means you need to have a path in the graph or NFA from the state for B to the state for a newly created state with the label as X. Okay, label as X. In that case, the last state is also a newly created state, and hence you need n number of states if n is the number of simples in the string X. So for all rules of the form B going to X, add a path from B to a newly created state with the label as X, and the newly created state to which the path is added, the last state must be made as a final state, and that's what we did. And I hope you followed. Otherwise, please watch it again and try to understand it with the help of an example production in the corresponding step. And with this, we are moving to the last slide of this lecture, where we are claiming that the language generated by the constructed NFA is exactly the language represented by the given right linear grammar. And if you want, you can use principle of mathematical induction to prove it. And if you are interested in, and if you have time, please try to use principle of mathematical induction to prove that the generated NFA with epsilon transitions accepts the same language as the given right linear grammar. So today we have learned an algorithm to construct an NFA with epsilon transitions from a right linear grammar. So it tells us that the language represented by any right linear grammar is a regular language, because there exists an NFA for accepting the language. Thank you.